today's video, we're going to define the mean of a discrete random variable. So firstly, let us come up with sort of an intuitive idea of where we're trying to arrive. The mean, as you might have heard about before in your studies of statistics in earlier years, the mean is meant to be representative of an average. And in the case of a random variable, it sort of represents this idea of a long run average of a random variable over many repetitions of that experiment. So it's often referred to as sort of the expected value, and it's meant to provide a summary statistic of sort of the central tendency of the random variable. Now, this idea that we're dealing with here is a bit, well, it's abstract. It's sort of more an linguistic definition so far. So what I want us to do is sort of revisit a generalized idea of a random variable. So let's say we have a random variable and it has the following probability distribution function. So let's say it takes values x1, x2, all the way to a maximum value xm. And we've encountered one of these distributions before because let's say as well that the probability that all of them occur, so for example, for the first observation x1, it occurs with probability p1. Then let's say x2 occurs with probability p2, and all the way up to the very final term, or the maximum value of this discrete distribution. Let's say it occurs with probability Pn. Another way we can write this sort of in a mathematical shorthand is Px of xi is equal to Pi for all I an element of 1, 2, m. That's a very fancy shorthand way of writing the distribution above. Now, here's where it gets interesting. Firstly, before we talk about this idea of an average, what do we mean by a probability? Well, like what does it mean by P1, X1 has a probability of P1? Well, really what this means is, let's say we were to conduct experiment n times, right? So a total of n times we run this experiment, and each time that we run the experiment, it is identical in the way that it occurs. Not identical in its outcome, but each time that we do the experiment, the probability that x1 occurs is the same each time we run the experiment, and the probability x2 occurs is the same as we run the experiment over and over. This is what we mean by identical experiments. Now, in this experiment, suppose we observe xi, right? So I'm trying to come up with a general form, xi, a total of ni times. Right, so out of the total n times that we run the experiment, for xi, so for example, for x1, we observe it ni n1 times. For x2, we will observe it n2 times, and for xm, we will observe that nm times. So what we really mean when we say after all of this is that the probability of pi is equal to the proportion of times that we observe the ith, or the number of times that we observe xi out of the total n times. So for example, for x1, the p1 here, as an example, is n1, the number of times we observe observation 1, divided by the total number of times that we run the experiment. Now, really, we're going to do something a little bit different here. Not only is that the case, it's actually a bit more formal than that. It's actually, by definition, the limit as n tends to infinity of this proportion. In other words, our probability pi of any of these occurring is what happens in the long run when we run the experiment n times, and then we observe the ith term, or the ith observation, ni times. Then we define the probability as, in the long run, what proportion of times do we observe I? In the long run. That's what we mean by n tends to infinity. So far, so good. So, what does this mean for a random variable, and what does this mean for averages and mean and expectation? Well, again, recall that x1 is observed n1 times, right? x2 is observed n2 times, and so on and so forth, up to xm. That's observed, nm times by our little experiment here. All so far, so good. Now, let's run this experiment a few times, right? So if we were to actually run it, maybe the first, an actual run, maybe what we get is x3, then we observe x2, then we observe x3 again, dot, 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 dot. And then after, the total number of n times, right, n simulations of the experiment, the final one is, say, x1. As an example of a run that we might be observing. But again, what we've said is that we want to work out the average of these numbers. This is what the mean represents. We want to work out the average of these numbers. Now, I could add them up one by one. I could say, x3 plus x2 plus x3 plus dot, 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 all the way to x1. I don't need to do that because I've already defined in my problem above. I've said within these n runs, we observe x1 n1 times, x2 n2 times, xm nm times. So I don't need to do that. So instead, to work out the average, and remember by definition, that average would be the following. XAVE would be x1 times the number of times you observe nx1 plus x2 times the number of times you observe x2 plus dot 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 plus all the way xm times the number of times you observe the mth observation, all over the total number of observations. This, by definition, is the average if we were to run the experiment a total of n times. Now, in shorthand, notice that this can be written as 1 over n, the sum of xi ni from I equals 1 to m. This shorthand here, or I should say, this shorthand here is really just a shorthand version of the sum up the top here that I've written. All right, so for I equals 1, you substitute the index I in here, you get x1 times n1, x1 times n2. Then you go to the next index here, I equals 2. That would become x2 plus n2. Here's your xn2 plus n2. You go all the way to m. That gives you your xm times nm here. So that is by definition. And then what we will say is that our definition of the expected value of x, the expected value of x is actually the limit as n tends to infinity of the average value of n repeated experiments. So let's do that now. That's equal to the limit as n tends to infinity of. Now I'm going to have the shorthand version. I'm going to rewrite it actually back as the old version. x1 times n1 plus x2 times n2 plus dot 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 plus x m times nm all over n. Limit as n tends to infinity of. Now, let's look at the first term here, and I'm just going to concentrate on the first term as well as the denominator. I can rewrite x1 times n1 over n. I can rewrite that as x1 times n1 over n. Just that very first term here. The second term I can rewrite as x2 times n2, I'll write it down, plus x2 times n2 over n. Put bracket out the front, plus dot 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 dot, plus the final term can be rewritten as xm times nm over n. And now we're finally getting somewhere here, because look, if we consider the limit of just the first term, if we think about how limits operate, well, x1 does not interact with the limit here, because as n approaches infinity, x1 stays the same. However, what does change is the second term. As the limit as n approaches infinity of this ratio here, n1 over n, we know what that is. We actually defined that above before. This limit here that we've defined is the probability pi that we defined earlier above, or p1 for n1. So then that first term actually just simplifies to x1 times p1. Similarly, if we were to look at how the limit interacts with the second term here, again, x2 is independent of the limit n, but n2 over n, we know how that it tends towards as n approaches infinity. That is the second probability. And this goes on and on and on up until the very last term, which is xm times pm. And here is what we are defining as our expectation, or our expected value. Now, here is I've sort of labeled some elements here, x1, p1, x2, p2. So I'm going to first put it in a more summation friendly way so that we don't have to keep writing this long version here, we can simply write that as xi times pi and summing that from the index I equals 1 to m. That's the first sort of simplification. And then the next simplification here that I'm going to do is I'm not going to rewrite it in this way, but I'm actually going to rewrite it in a more generalized sense so that we don't have to rely on pi's and xi's. And I'm going to say, well, it's x times px of x, right? So it's the value of x, times its respective probability mass function, right? X times its respective probability mass function over, and we sum across all of x in the support of x. And then this definition here is what we will use for calculating the expected value of a discrete random variable. And this is hopefully gives you an intuition as to why we use this definition in the first place, if it's something that you've seen before. And typically what we can do is sometimes we write this as mu x, or the expected value of x in these brackets. That is how we formally define it. Now, let's look at an example that might be helpful to solidify our understanding. Suppose we're rolling a die. So let's say that's our context. Rolling a dice or a die. Now let's think of the probability distribution function here. So in terms of our x values, we can get 1, we can get 2, we can get 3, we can get 4, we can get 5, and we can get 6. And in terms of our probabilities, we assume, because it's a 6-sided die, and we assume that each face is equally as probable, that the probability that each of these occurs is 1 on 6, and otherwise px of x is equal to 1 on 6, 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 and 1 on 6. This is a standard, very standard example of something we could look at. Now, in a few seconds, we're going to take a look at, well, is it really 1 on 6? Well, we'll get to that in a sec. But first, let us calculate the expected value of this particular random variable. So, in this case, the expected value of x, denoted as e brackets in x in brackets, again is going to be defined broadly as the sum of x in the support of x, so the sum across all values of x in the support of x times px of x. In other words, we look at the first term here, the 1 and the 1 on 6. We multiply those together, 1 times 1 on 6. Then we look at the next set, 2 times 1 on 6. 2 times 1 on 6. Plus again, look at the next set, 3, and it has a probability of 1 on 6, so it's 3 times 1 on 6. And we can continue this up until the very final term, times 1 on 6, plus all the way to 6 times 1 on 6. And if you calculate this out, you get a value of 21 on 6, or if you were to simplify that down, that becomes 3.5. Now, this is all good and well, but does it mean anything in reality? So what I'm going to do now is I'm going to bring an Excel spreadsheet to solidify what we really mean when we take this expected value. And before you worry too much about whether you have any Excel skills or not, I'm not too concerned about the functions that are involved here. I don't want you to get too bogged down about the functions I've used, but I do want you to understand, at least at a very small level, what's happening, or at more of a understanding level, what is actually happening in each of these particular cells. So, in this first column here, this I've tried to simulate the results of a dice experiment, or rolling a dice. So here, for example, is roll 1, and we've observed a 2. Now, I've used the Excel function here between 1 and 6. And what that ran between 1 and 6 does is it simulates a dice roll. It's saying, the numbers between 1 and 6, what do you get randomly? Between 1 and 6. And I've simulated that quite a few times. In fact, if you go to the end here, I've simulated the dice roll about 1,000 times in this whole sort of experiment. And then each of these comes up with an observation, and Excel is able to randomly generate numbers from 1 to 6, and you see them here. In this next set of results here, what I've done is I have calculated the relative frequency after each roll. So for example, in the very first roll, you'll notice that the observation is 2. And therefore, the frequency after the first roll is saying I've observed the roll 2 once, and I've observed everything else no times, 0, 0, 0. After 2 rolls, I've done a 2 and a 5. So you'll see there's a 1 marked at the 2 spot, and there's a 1 marked at the 5 spot. And, after, say, 10 rolls, and you've got a few rolls here now after 2, 5, 4, 6, blah, 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 you can see here that there's a 3 in the 2 column after 10 rolls. And all that is telling us here is that if you were to look at all the observations so far, you'd see a 3, a 3, a 3. You'd see, sorry, we're looking at the 2 spot. So you'd see 2, you'd see 3 2s, and that's true in the highlighted state there. Hence why we see a 3 as the frequency. Now, as we move along in this part here, what we do after the 10 rolls that we have, 1, 3, 3, 1, 1, 1, we actually calculate the relative frequency. And that relative frequency is basically telling you, out of the 10 rolls that we've just had, what percentage of them are a 2? And you can see it here, in fact, because, for example, when we look at roll 2, after 10 rolls, you've got a 3. You've got a 3 here. 3 out of 10 gives you 30%. So that's what it's sort of trying to get to here. And that can continue onwards and onwards. Here is the first interesting part of this probability experiment that we're running. Let's have a look at what happens as we continue onwards. In other words, what happens is the number of rolls gets bigger and bigger and bigger and bigger. Let's have a look. You'll notice that they start coming out to be close. In fact, very close. They start all round coming out at about, 17%. It's not exact, right? So some are a little bit higher, some are a little bit lower, but you can see compared to the start where, you had nothing too close here, 33%, 11%, it's quite divergent. By the time you get to 1,000 rolls, already we're starting to see very similar probabilities. What that really is representing, as you saw before, is, as n, or as the number of experiments increases and increases, you get closer and closer to the true probability. And the true probability in this case, 1 on 6, if we were to calculate that as an example here, and we can do it as we'll take out the calculator here. 1 divided by 6 is about 16.6, right? So it's sitting around 17%. We're not exactly there, but give or take, we're roughly there. Now I want us to instead, by the way, here is what that looks like plotted on a graph. You can see here, this is I believe it's the relative frequency for roll 1. And this is just a plot after every single, or after, say 145 rolls, this is the relative frequency. After 307 rolls, this is the relative frequency, and so on and so forth after the number of simulations. And you can see here, as in the first part, or in the first sort of, 200 rolls, it's not really collapsing, or it's not really converging to any sort of long-term probability. But as we go further and further and further in, this probability, and don't be fooled by the scale here, this probability is almost flatlining to around a value of 1 on 6. And that's what we sort of mean as the probability converges. That's what we mean by as n tends to infinity, we observe that this probability becomes closer and closer to the true probability, which we think is 1 on 6. Let us also look at the empirical expectation, or I should say the empirical mean. So all this function here does, by the way, if I were to, look at after a few rolls, this function here takes the average of the number of rolls. So it looks at the first 11 in this particular instance, and it takes the average value that we observe. Now you can see for the first few, it's 2, 3.5, 3.7, 4.3, 4.3. But look what happens as we get larger and larger and larger. We almost converge exactly on 3.5, which is exactly what happens to be, and I can also demonstrate that to you graphically if I look at the next graph here. This is a plot of the average of the number of dice rolls as we increase the number of simulations. And what do you know? It ends up being very close to the theoretical average. This is what we mean by expectation. This is the power of as we repeat an experiment, what do we get to our mean? Thank you for listening into this video explaining the mean. In the next video, in the part 2 of this series, we're going to look at a few more examples and perhaps even another mathematical way of computing the mean. Thanks for watching. Hope to see you in the next video.